Let's review a little bit about the definitions of strong and weak acids. So strong means that an acid will donate nearly all of the H plus ions into the solution. So essentially it is ionizing 100% into the water. This also makes it a strong electrolyte, meaning that it will conduct electricity. So strong has to do with the percent that our acid ionizes. If we want to find the acid concentration, the H3O plus concentration, it is going to be equal to the concentration of the strong acid. Remember, the brackets mean molarity of that particular compound. So if it's 8, the brackets are around the H3O plus, that's our H3O plus concentration. It is equal to that of the strong acid. Breaks up nearly 100% in solution. If we are talking about a weak acid, weak acids, they donate only a small fraction of their H plus ions. So it has nothing to do with the overall concentration of the weak of the acid being strong or weak. It has to do with how much of it ionizes into the solution. So most weak acids, they stay mostly as the molecule and only donate a very small amount of H plus to the water. So much less than about 1% ionizes. So the H3O plus concentration is much less than the overall concentration of the weak acid. An example of a weak acid is hydrofluoric acid. When hydrofluoric acid is in water, most of it is staying as the molecule HF. Only a very small percentage dissociates into ions. Now the reason for this has to do with the attraction between the H plus and the anion. So if it's a strong acid, it means that it's a weak attraction. It easily breaks apart into the H plus and the generalized A minus, so the anion with a negative charge. If it's a weak acid, it means that it has a very strong attraction for that H plus and the anion that makes up the weak acid. Now I know this can be counterintuitive, that it sounds are difficult to remember, that strong acids have a weak attraction, but if we think about it, it has to have a weak attraction to break apart easily. Weak acids have a strong attraction because it's harder for them to break apart. The way that we measure how strong or weak an acid is by looking at the acid ionization constant. This is the equilibrium constant that tells us the strength of an acid. So we represent it by K with a small subscripted A, representing acid. So our equilibrium constant is found by the addition of water to our weak acid. The expression is the H3O plus concentration times the concentration of the anion divided by the overall concentration of our weak acid. The larger that our Ka is, the stronger the acid. If we have a strong acid, it will not have a Ka value. If it is a weak acid, we can have a wide range of Ka values. Everything from chlorous acid, which is 10 to the minus 2 for our Ka value, all the way up to phenol, which is 10 to the minus 10. And so if we have a weak acid, there are tables that allow us to look up these Ka values, so our equilibrium constant for our acids. Water is amphoteric, which means that it can act either as an acid or a base. So that means that there are a few ions that are present at all times. It can react with itself, one of the water molecules acting as an acid, one of the water molecules acting as a base, forming a conjugate acid of H3O+, and at the same time it forms a conjugate base of OH-. Now, when these form, it contains both the H3O+ and OH-, and if it's just water, they are in equal amounts. So the amount of H3O+ equals the amount of OH-, and in water, that concentration is 10 times to the -7th molar if we are at 25 degrees Celsius. Contains equal amounts of H3O+ and OH-. To find the equilibrium constant expression for water, it is equal to the H3O+ concentration times the OH- concentration divided by the reactants. However, the reactants in this case are a liquid. So because it's a liquid, it is not contained in our equilibrium constant expression. So we call this particular value for water the ion product of water, or the dissociation constant for water, and represent it as Kw. It has a known constant value at 25 degrees Celsius of 1 times 10 to the -14. We get this by taking 10 to the -7 for H3O+ times 10 to the -7 for OH-. As our H3O+ increases, so as our substance becomes more acidic, the OH- is going to decrease in order to keep this equilibrium constant expression, or the value constant. So they're inversely proportional. The H3O+ concentration is inversely proportional to the OH- concentration. So as our H+ concentration is larger, our OH- is smaller. As the OH- concentration increases, the H+ gets smaller. Now, if H+ is dominant, that means that we are in an acidic solution. If the OH- is dominant, that means we're in a basic solution. And when they're equal, we are neutral. So all of our solutions, all the aqueous solutions, contain both H3O+ and OH-. If our H3O+ is greater, that means that it's an acidic solution. If the OH- concentration is greater, that means it is a basic solution. So here's an example. Let's calculate the OH- concentration when we know the H3O+ concentration. So we're going to see if it is acidic, basic, or neutral. So we know our equilibrium constant expression, or our Kw for water, is the H3O+ concentration times OH-. Because Kw is a constant, 1 times 10 to the -14, we can substitute that in, and our H3O+ concentration, 1.5 times 10 to the -9 molar, to calculate our OH-. We'll divide both sides by the 1.5 times 10 to the -9 molar concentration of the hydronium ion. To find our OH- concentration, of 6.7 times 10 to the -6 molar. Now, if we compare these two concentrations, we have 10 to the -6 and 10 to the -9. The 10 to the -6 is larger, so our OH- is dominant. means that it is a basic solution. Because this is less than 10 to the minus 7, we already could tell before doing any calculations that it should be basic. Here's a practice for you. Pause the video to determine the H3O plus concentration when you're given the OH minus. We're going to look at the Kw is equal to the H3O plus times the OH minus. We know the OH minus, so if we divide both sides by OH minus, we can get the H3O plus by itself. So if we take the Kw divided by OH minus, that is equal to our H3O plus concentration, the hydronium ion. So Kw is a constant, 1 times 10 to the negative 14 when we're at 25 degrees Celsius. We divide by the OH minus, and we find that our H3O plus concentration is 4.0 times 10 to the minus 6 molar. Now, if we compare these concentrations, 10 to the minus 6 is larger than 10 to the minus 9, so this is an acidic solution. We would be able to tell this already because our value for OH minus is less than 10 to the minus 7, meaning that this would be an acidic solution.